Good afternoon everyone, myself Subhajit Guha, Faculty, Department of Computer Science, Barakpur Ashokuri Shandhat College. Today I would like to teach the following topic, that is the fundamentals of Boolean Algebra and Boolean function. So in the theory of computer science, the foundation of this subject that is built up through the subject of mathematics, and mathematics deals with logic and analytics. Analytics means arithmetic analytics or any kind of computational analytics. So in case of arithmetic, we can use various arithmetic operators or operations like addition, subtraction, division, multiplication, modulation, etc., etc. But in case of logic functions, we can use the concept of the Boolean algebra. So famous mathematician George Boole first invent this abstract algebra via some Boolean logic based on the binary decisions. So here I am explaining the concepts of Boolean algebra. So in that case, logic means a statement having binary decisions. So what is decisions? Let's take an example. I hope that I am not going to college today. So okay, is it the right statement or wrong statement? If seriously I am not going to the college, so it is right. So the return value of this statement is yes, or true, or 1. If I am not going to school, in that situation the statement is going to false. So it is a 0, it returns 0 or false statement. So the Boolean algebra deals with basically two binary forms, that is 0 and 1. And it is a systematic way of expressing and analyzing the operation of logic circuits. So first of all, if we would like to explain the concept of Boolean algebra, first we have to know about the concepts of set. So what is a set? Set means set is a well-defined collection of distinct objects, and we can represent a set via some Venn diagram. So please follow the board. Let we take, this is a set. This is a set A, and this is another set B. For example, the set A holds certain elements like 1, 2, 3, 4, and set of B consists another element, that is -1, -2, -3, -4, etc. So here we are noticing that every element in the set is distinct. Okay, so set is a well-defined collection of distinct objects. In case of Boolean algebra, the universal set is a concept where, suppose in a given situation, that every set of interest in our real world is a subset of a fixed non-empty set. So suppose in the real world situation, if we take our world as an example as an universal set, and if our house, our locality, the chair, the bench, the room, the animal, the people, we take the element of this particular set, so the entire world will be treated as an universal set, and this object like with the subset of this particular universal set, and the universal set will be named as S. So inside an universal set there must be exist number of sets. Here A and B are two sets, that is the subset of this universal set S. So A is the subset of S and B is another subset of S. So from here, if we take A, hold some examples, like we take here X and Y. Okay, so let S is equal to X and Y. Here there exist 4 components, that is 5, that is null, that is single element X, that is single element Y, and that is single element as XY. So those are the components of the following sets. So according to the Boolean algebra, the set element is particularly defined. As it is mentioned, it follows the rule of binary, so it helps the ranging from 0 to 1 or 0 or 1. Now I am explaining the construction of Boolean algebra. So here algebra of classes consists of the power of 2 to the power s set of subset of S together with two operations like conjunction and disjunction. So the conjunction means that is set intersection and the disjunction means that is set union. So here exist 5 operations that like B is equivalent to 2 to the power S, where 2 to the power S is the power set of this particular universal set, and another operation that is plus, and this is equivalent to union, or this product that is equivalent to intersection or this, and the last one is the zero that depends on that is the phi or null set, and 1 that is the set itself. So a Boolean algebra can be defined as like following, that is B or and 0 1. This is the system of a Boolean algebra. Here B means 2 to the power s, so we can write it down, that is 2 to the power s plus dot 0 and 1, and that constitutes the Boolean algebra. Now the fundamental operations of Boolean algebra are there. There are 3 kinds of fundamental operations. First one is a Boolean sum, is another name as disjunction. Next one is a Boolean product, that is the conjunction, and last one is the Boolean complement or negation. So now we are taking the diagram, Venn diagram, to explain the operations like x is this set and y is this set. Let's, from this picture, from the first picture, we are noticing that is x intersection y, that is this part, which are the common part of x and y that will be derived by x intersection y, or it can be represented another way, that is x product y. And if we take the x union y, that divides the entire set, that is x plus y, and another is the complement of x or x prime, that is as the universal set minus this particular number. So in the Boolean domain, the set varies from 0 and 1, that means 2, either 0 or 1. So in that case, any function that is 0 0 0 1 1 0 1 1, in case of 2 variable, we can generate from it. So the Boolean sum or logical OR operations is like that, that is 1 plus 1 is equal to 1, 1 plus 0 is equal to 1, 0 plus 1 is equal to 1, 0 plus 0 is equal to 0. So from the set, if x is equal to 1 and y is equal to also 1, then we get this value. 1 plus 1 means this entire set, that means 1. 1 plus 0, here x is there but y is not there, so it is x is equal to 1, so this is 1. 0 plus 1, here x is equal to 0 means that is 0, but y is equal to 1, that is 1. And in case of x is equal to 0 and y is equal to 0, both are 0. that no sex exists. So in that case, we can tell that the Boolean sum or disjunction operation is follows there. There is another operation that is called the Boolean product, and it is the opposite form. It's like that: 1.1 is equal to 1, 1.0 is equal to 0, 0.1 is equal to 0, 0.0 is equal to 0. And last one is the complement. In that case, the Boolean complement or negation denoted by tilde sign or not or by prime sign and has the following values, that is 1's complement is equal to 0 and 0's complement is equal to 1. But how? In the Boolean domain, there are two numbers, that is 0 and 1. So in this domain, the universal set is 1 because highest number is 1. So if we want to calculate the complement of 1, that is means s minus this number 1. So here s means the universal set is 1, 1 minus 1, that is equal to 0. Similarly, complement of 0 is equal to s here, that is 1 minus 0 is equal to 1. Hence, we can conclude that the complement of 1 is equal to 0, but complement of 0 is equal to 1. So here are the three operations we can find, that is first one is Boolean sum, that is plus or, and Boolean product, that is dot and Boolean complement, that is C or this or prime, that is not. So and or not are basically the three fundamental operations in Boolean algebra. Now, Huntington's discovered some rules based on Boole's mathematical work, and it is known as the Huntington's postulates. So according to the first postulate, that is the commutative law. So what is the commutative law? If x and y is an element of B, then we can write x plus y is equal to y plus x. So let we take an example. X is a set and y is another set. If we take the union of these two sets, that is x plus y, that is equivalent to y plus x2. As the same, if we conclude that x dot y, that is the x Boolean intersection, is equal to y dot x, that is the y intersection x. This is the first law of Huntington's postulate. The second law is the distributive law. Here we consider three elements, that is x, y and z is an element of Boolean set, that is B. The first rule is that x plus y dot z is equal to x plus y dot x dot z, and the second rule is that x dot y plus z is equal to x dot y plus x dot y. And the third element is the identity, and it is important because identity means how can I identify a particular element. So if we use the addition operation, so here the identity element is 0, because from the addition operation, if we add 0 with this particular value, then we return the same value. So 0 is the identity element here. As the same in case of dot, if we take 1 dot is equal to x, so 1 is the identity element. The fourth law is the complements, that is x plus x prime is equal to 1 and x dot x prime is equal to 0. From this set we can conclude out that x is a set, y is another set. Let me take an example. Here x is only set. Suppose X is the only set within this universal set S. So X means this entire body. X prime means S minus X, that is equals to X prime. So X plus X prime means that is equals to X plus S minus X, that is X eliminate and we get the entire universal set. As it is in Boolean domain, so the value of S is equal must be 1, because 1 is the maximum number in this Boolean range. That's why we called S that is equals to 1. So X plus X prime is equal to 1. As the same, if we take another example, X dot X prime, what does it means? X dot S minus X, that is X 1 minus X, X means 1 now, so X dot 1 minus X dot X, that is X minus X dot X means X, that is equals to 0. So that's why X dot X prime is equal to 0. Okay. Now these are the following useful laws that can be applied in Boolean algebra. That is, first law is the associativity, is called associative law. From this law we can deduce that X plus Y plus Z is equal to X plus Y plus Z, and the second principle is that X dot Y dot Z equals to X dot Y dot Z. Next, the idempotency. From this law we can deduce X plus X is equal to X, because if X is only the set of this universal set, that is, if we conclude if we include another X, so X become the unit one, so X plus X is equal to X. As the same, if we take X dot X and we get this another value, that is equal to X. Next is the absorption law, that is X plus X dot Y, that is equals to X. This means if we common X, that is Y, X dot 1 plus Y, that means 1. Now if we take Y dot Y plus Y prime plus Y as 1, if we take Y plus Y plus Y prime, X dot Y plus Y means Y plus Y prime, that is equals to Y plus Y prime is equal to 1, that is equal to X. So from absorption law we can get X plus X dot Y is equal to X, and from another principle X dot X plus Y is equal to X. From involution we can get the double prime concepts. So the prime of an element over prime of this number is called the mother number. So the complement over complement of a number is called the mother number. Means if we complement certain element like X, and that is the whole complement or over complement, that means X double prime, that means X. So here that is S minus X, this prime, so this prime means S minus X plus X, that is SS eliminate, we get the value X only. Okay, so this is the involution formula, and next one is the consensus, that is xy plus x prime z plus yz, that is equals to xy plus x prime z, and other properties like 1 plus x is equal to 1 and x dot 0 is equal to 0. So those are the axioms or laws that will deduce from the Huntington's postulates, and we can use this evaluation in our following sections. So the next is another principle, and it is very important principle, that is the De Morgan's theorem. So there exist two theorems of De Morgan's. The first theorem is that if a plus b the whole complement, that is equals to a complement dot b complement. Number 2 is that a dot b whole complement, that is a complement plus b complement. So if we take a tabular form, it's called a truth table, and if we put the value of a and b, so we get is like that: a b, that is a plus b, that is a dot b, that is a plus b complement, that is a dot b complement, that is a complement dot b complement, and last one is a complement plus b complement. So here are 4 combinations, that is 0, 0, 0, 1, 1, 0 and 1, 1. So if we take this value, this is OR operation, this is logical AND operation, and if we take another value, that is a prime, that is NOT operation. So this value will be, that is 1, 1, 0, 0. A plus b means 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1. And means 0, 0, 0, 1. So the a plus b complement means the complement of OR. That means that is 1, that is 0, that is 0, that is 0. And a dot b complement means the complement of AND. So it is called that NOT OR, and this is NOT AND. So from a plus b complement, that is 0 means 1, 0 means 1, 0 means 1, 1 means 0. That from this equation we can find that a prime dot b prime, that is a prime means 1, as a take, if we take the b prime, is the following like this. It is b and it is a prime, that is 0, that is 1, that is 0, 1, 0, 0, sorry, that is 1, 1, 0, 0, that is 1, it is 0, 1, 0. So if we take, that is a complement means 1 dot 1, that is means 1, 1 dot 0 is 0, 0 dot 1 is 0, 0 dot 0 is 0, and a complement plus b complement means 1 plus 1, that is 1, 1 plus 0, that is 1, 0 plus 1, 1, 0 plus 0, that is 0. So if we follow the following table, so we can deduce that a plus b prime, that is this one, is equivalent to a prime dot b prime. So these are same. And similarly, a dot b prime, this one will be same as this one. So we can deduce the proof that according to the De Morgan's theorem, that is a plus b whole prime, that is equals to a prime dot b prime, and a dot b whole prime, that is equals to a prime plus b prime, and we can find two operations like NOT OR, and another operation, that is NAND, and its other name is called the Schaeffer function, SHEFFER, Schaeffer function, and it's called the Nicode function, NICOD, Nicode function. Next comes to the principle of duality. It means the dual of a Boolean function or expression is obtained by interchanging the Boolean sum and Boolean product. So that means if we take an example, that is x dot y plus z, if we take the dual of this following expression, we get the dot should be replaced by plus and plus should be replaced by dot. So that means that comes x plus y dot z. So it is the dual of this following function. If we take f1 and this is f2, so we can say that f1 is to f2, that is the dual, and it is deduced by the fd. So dual function denoted by fd, that doesn't depend on the particular Boolean expression used to represent the function f, but this means the interchanging of the Boolean sum to Boolean product and Boolean product to Boolean sum. There is another function and it is called the exclusive OR function, or another name is the antivalence function, and another is the exclusive OR or equivalence function. What does that mean? It means the exclusive OR XOR, or name is big XOR, simply XOR, and another function is the exclusive NOR, that is X NOR or N XOR. And the operators are like that. XOR means this symbol and XNOR means this symbol. So A XOR B, and here A XOR B, this complement, or it is equivalent to A XNOR B. So there exists four combinations 0, 0, 0, 1, 1, 0 and 1, 1. XOR returns always truth value if two values are different. Two values are different. From this example, we are noticing that the value of A is 0 and B is 1. Here XOR returns value 1. And if A is equal to 0 and B is equal to 0, it is always return 0. As the same, if A is equal to 1 and B is equal to 1, it will always return value 0. But in case of A is equal to 1 and B is equal to 0, it will always return value 1. So in that case, that is 0, 1, 1, 0. And this XNOR function, this is XOR function, and it is XNOR function, that is its complement. So that means 0 means 1, 1 means 0, 1 means 0, 0 means 1. So according to this view, we can notice that the antivalence function, that is exclusive OR, that will be calculated by this particular logic, and we get that A XOR B, that means A complement B plus B complement A, and from A in XOR B, that means A and B plus A complement and B complement. So these are the two functions, that is exclusive OR and exclusive NOR. So till now we have taught the following functions. Number 1, that is OR plus, that is AND or dot, that is complement or prime or C, that is NOT. Number 4, that is NAND, that is NOT plus AND. Number 5, that is NOR, that is NOT plus OR. And number 6, that is XOR, that is antivalence. And number 7 is N XOR, that is equivalence. So this operator is plus, this dot, this NOT means complement, and this NAND means whole prime, nor means whole prime of some two ORs, and antivalence means XOR, and equivalence means XNOR. So these are the 7 Boolean functions which will be applicable in our further sections. So these are the operations. I have already told about that. The following example, that XY, this is a X complement, that is X plus Y, that is OR, that is X dot Y is AND, X plus Y whole complement, that is NOR, X dot Y whole complement, that is NAND, X XOR Y, and X XOR Y, this complement over complement, that is N XOR. Now I am coming to the part that is the Boolean function. I am discussing the Boolean function. So let's take an example. If we take X as a value, that is equals to 1, so we may call it as a constant. If we take X is equal to 2, it is also a constant. But if we take Y is equal to X plus 1, that Y is not a constant. Here Y is a variable. That means if we take the value X is equal to 1, so that means Y is equal to 2. If we take the value X is equal to 2, that is 2 plus 1, Y is equal to 3. So Y is a function of X. So we can write that Y is equal to Fx. So in Boolean domain, an invariable Boolean function, that means a function that maps this following variable. Here B means 0 and 1, and N means number of literals in present that map to 0 and 1. Hence, it is called the Boolean function, a function from B to the power n, the set of x1 to xn, where x is an element of this B, and so B is called a Boolean function of degree n. Here degree means the number of variable. So now take an example. So if we take x1 and x2, two variable, and it will be combined is like the way, that is 0 0 0 1 1 0 and 1 1, and it will map only either 0 or 1. From this function value, that is f of x1 and x2, we get this value, that is 0 0, the value is 0. From 0 1 we get the value is 1. From 1 0 we get the value is 1, and from 1 1 we get the value is 0. So here the 0 1 and 1 0 will map to the 1 value, and 0 0 and 1 map to the 0 value, and this is the overall domain, that is 0 0 0 1 1 0 1 1, and 0 and 1 1, 0 0 and 1 1 map to the 0, 0 1 and 1 0 map to the 1. So this is the function, that is y is equal to f of x1 x2, and mathematically this is the XOR function. So now if we take one variable, that is a, the two value is either 0 or 1. So from the operation we can get that a plus a is a function, a dot a is a function, a prime itself is a function, a plus a prime itself is a function, a dot a is a function, 1 plus is a function, 1 dot a is a function. So there exists total number of functions. And if we take two variables, that a and b, so here are 4 combinations, that is 0 0 0 1 1 0 and 1 1, and from we get this kind of functions. Now the questions come to our mind, that how many functions can be generated in case of certain variables, number of variables. For two variable functions, if we take x and y, two variables, we can get 0 0 0 1 1 0 and 1 1. So there are 4 functions, sorry, not functions, they are combinations, 0 0 0 1 1 0 and 1 1. So from these above combinations we can generate extra 2 to the power n functions, means another 4 functions. That means it can generate 4 functions, it can generate 4 functions, it can generate 4 functions, it can generate 4 functions. So above all, from x, y, y variable we can get that 2 to the power 4 functions, that is 16 functions. And if we take one variable like x, we can generate only 4 functions. So here is examples, how many different Boolean functions of degree 1, degree means the number of variable, that is one variable, are there exist f1, f2, f3 and f4, there are 4 functions with one variable. And this is the 2 variable Boolean functions, and there exist 16 functions. That is 0, 0, 0, 1, 1, 0, 1, 1. From that we can generate 16 functions. So how many different Boolean functions of degree n are there? So there are 2 to the power n different combinations of those zeros and ones in n variable function truth table. Okay, so a Boolean function is nothing but an assignment of 0 and 1 to each of these 2 to the power n different n rows. So therefore we can there must be exist 2 to the power n number of Boolean functions can be generated with n variables. So here is an example that the elementary Boolean function with 2 variables, and this is like that. If we take x1 and x2 these value, we can realize these 2 values by using these kind of functions. Now I come to the point, how to evaluate Boolean functions. To evaluate a Boolean function with the help of a table is called a truth tables. So in case of truth tables, we take some Boolean variables. Here we are taking x, y and z, and there are 8 combinations are there up to 7, 0 to 7, that is the 8 number of variables are there. And from function 1, that is x, y, z prime. That means x, y, z prime means x means 1, y means 1, z prime means 0. So in case of 1, 1, 0, that is x, y, z prime. Okay. From this case, f1 generate only truth values. So in that case, I am writing 1 here. According to this f2, that is x plus y prime z. It's like that. It's like that. F2, that is 0, 0, 1. F2 here 0, 0, 1 and 0, 1, 1 and 1, 0, 0 and 1, 0, 1 and 1, 1, 0 and 1, 1, 1. So these terms are involved to generate the f2 function. So 0, 0, 1 means x prime y prime z, 0, 1, 1 means x prime y z plus x y prime z prime plus x y prime z, x y z prime, x y z. So from that, if we evaluate this following expression, we can get this value, that is x plus y prime z. How? If we take that is x prime z, that is y prime plus y. From this we can get x y prime, that is z plus z prime, plus if we take these two value, that is x y, that is z plus z prime. So that is x prime z plus x y prime and x y, because y plus y prime is equal to 1, z plus z prime is equal to 1 and z plus z prime is equal to 1. From that we can use that x, that is y prime plus y, and we get that is x plus x prime plus z. So this how we can evaluate the following functions. So F3 and F4 are left for exercise. Please try at your home. So now, to represent the canonical form of a Boolean function, we are taking two terms, that is sum of in terms of sum of product, that is SOP, and product of max term or product of sum, that is POS. SOP means the mean term means at the end terms means the product terms. Okay, so here are 4 terms there, that is x dot y prime, x prime dot y, and x prime dot y prime. In case of, there are 4 terms are there in case of 2 variable functions. And as the same way, this is the max term or odd terms, and this is like that, x plus y prime, x prime plus y, and x prime plus y prime. Now, these are the set of min terms that is designated by small m0 to small m7, and these are the max terms or odd terms, that is capital M to M0 to capital M7. Now, what is the relation between min term and max term? They are complement of each other. The last line is that thus mi is the complement of mi. That means if we take an example, that is m2 is equal to x prime y and m2 is equal to x dot y prime, that means if we complement of m2, we get the this m2, and if we complement this m2, we get this value. So that means min term is the max term's complement, and max term is the complement of min term. So this is an example. This is the chart of min terms, and this is the chart of max terms. Here we are looking that the diagonal ones are the exist, and rest of themselves is occupied by 0. Here the reverse case, the diagonals are occupied by 0 and rest of them are occupied by 1. So it's the complemented form of the max term. Now, min term and max term can be represented in standard form. One is the SOP, that is sum of product, and another is the product of sum, and we can write the following formula is like that. The SOP is represented by f is equal to summation over min terms, and the POS, the product of sum, will be represented as the I of the max terms. So this is the nomenclature to represent min terms and max terms. Now to the point, minimization of Boolean function, and that is very important because we have to eliminate the redundancies which is generated to derive the Boolean expressions. Number 2, to avoid using of redundant hardware cost. If we want to reduce the hardware cost, then we have to eliminate the redundant expressions, and this reduce circuit cost for less expensive hardware implementation, and this is our ultimate goal. That's why we are evaluating this example function is like that by using the Boolean axioms. This is an example. So if we take a function that is f is equal to a prime b prime c plus a dot b prime c prime plus bc prime plus b prime c plus bc, that will be derived like that. The outcomes is only a plus b prime c, and now we are applying here this kind of Huntington's axioms, that is the complements law, identity law, and absorption law, and we get this following output, the reduced expression. And this is same as the max term also, that is POS form, that is f is equal to I of 0 to 3, and it will be squeezed in that way. The result is like that, a plus c dot a plus b prime. Now these are the exercise. I'm taking some of them and do it, evaluate just one of two. For example, if we taking example 1 means that is x dot y prime plus x dot y plus y dot z. That means we have to evaluate this statement by using the Huntington's postulates. So that means x, if we take x common, that is y prime plus y, that is yz, and we can get y plus y prime is equal to 1 plus yz, that is equals to x plus yz. If we take example 2 like that, a prime bc plus a prime b prime c plus a b c prime plus a b prime c. Right. So if we take a prime c, that is b plus b prime. If we take a c prime, we take b plus b prime. So that is a prime c dot 1 plus a c prime dot 1, that is a prime c plus a c prime. We can write it down, a XOR c. So this is the optimized expression. As the same, if we take example 4, example 4 means it is the standard form representation, that is function of a, b, c. That means summation over m of, that is 1, 4, 5, 6, 7. So in that case, the mean terms are involved, that is 1, 4, 5, 6, 7. 1 means 0, 0, 1. 4 means 1, 0, 0. 5 means 1, 0, 1. 6 means 1, 1, 0. 7 means 1, 1, 1. That means a prime, b prime, c. That means a, b prime, c prime. That is a, b prime, c. That is a, b, c prime, that is ABC. With the help of these literals or these mean terms, we can deduce the following expression. So from the first statement we can like that is ABC. If we take this one, so that is called AB, because c prime plus c is equal to, that is AB. If we take these two, that is AB prime, so we get plus AB prime and plus A prime B prime C. So this is the optimized expression of this following Boolean function. Now a systematic approach to minimize the Boolean function was invented at the year of 1953 by Maurice Karnaugh as a refinement of Wedge diagram. Wedge is another mathematician. He was proposed a diagram. Maurice Karnaugh was developed this proposed approach at the year of 1953. This is called the Karnaugh Map Technique. So maps are used to simplify real world logic requirements so that it can be implemented using a minimum number of Boolean literals. Once minimized, canonical SOP and POS form can be implemented directly using basic logic operations. So in a map has 0 and 1 entries at different sectors. It provides grouping together Boolean expression with common factors and eliminates unwanted variables. So in a map there exists 2 to the power n number of cells. So if we take n number of variable maps, so we get 2 to the power n cells. If we get 3 variables, so we get 2 to the power 3, that is 8 number of cells. If we get 4 variables, so we can get the 2 to the power 4, that is 16 number of cells. So a Karnaugh map is suitable for 2 variable to 6 variable, because if we take another more variable, the map size will be expanded, and we don't have any large RAM space. That's why you can save only 2 to 6 variable only. So these are the map structure. That is the 2 variable map, that is this one, that is a 3 variable map, and that is the 4 variable map. In case of 2 variable map, that is 2 to the power 1 is equal to 4 number. So these are the Keymap structure. The first one is the 2 variable map. Here 4 number of cells are there, that is 2 to the power 2 is equal to 4, and here 2 to the power 3, that is 8 number of cells are there, and there is 2 to the power 4, that is 60 number of cells are there. So if we observe this map, we are noticing that the sequence number across the top of the map is not a binary sequence. Here 0, 0, 0, 1, 1, 1 and 1, 0, that is not a pure binary sequence, rather it is a gray code sequence. So gray code sequence only change one bit as we go from one literal to another literal, unlike the binary number sequence. It means the adjacent literals will only vary by 1 bits. So this is the gray code generation algorithm. So in that case, if we take two variable gray code, we can simply write 0 and 1. And then we can draw a mirror and let's reflect the mirror, that is 1, that is 0. And the above half will be padded by 0, that is 0, 0, 0, 1, and that is lower half will be padded by 1, that is 1, 1, 1, 0. So this is the two variable gray code sequence. So that's why in Keymap, if we are using like that, that is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So this is the gray code sequence. So this is the formula of gray code generations, that is this way. For n variable binary number, the gray code will be reduced in this way, that is gn is equal to bn, gn minus 1 is equal to bn minus 1 XOR bn, and z0 is equal to b0 XOR b1. With the help of this approach, we can generate the gray codes. It is the two variable gray code generator. This is the three variable gray code generator, and these gray codes are used to design a Karnaugh map. So these are the SOP representation and POS representation of K-maps. K-maps are like that way. This is a three variable K-map. Sorry, I am writing the first two variable K-map or Karnaugh map. This is two section. This is 0, this is 1, this is 0, 1, this is 0, 1. The value is 0, value is 1, value is 2, that is 3. This is a two variable Karnaugh map. If we take the three variable Karnaugh map, there will be 8 cells. That is, if we take A and BC, that is A prime, that is B prime, C prime, B prime C, B C, B prime, B prime C. That is 0, that is 1, that is 3, that is 2, that is 4, that is 5, that is 7, that is 6. That means, this means like, that is 0, 0, that is 0, 1, that is 1, 1, 1, 0. And for 4 variable map, there will be 16 number of cells. That is A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. That is 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, and 14. And now look at that SOP representation means, and POS representation, in case of POS representation, we can write the max term in this box. So in case of POS representation, we can write only once, just once, and rest of them are 0. But in case of SOP representation, we can write the min terms as 1 and in case of US representation we can write the 0. And it is the SOP representation. Actually the map is like this structure, is a cylindrical structure. We can rotate this map, we can fold this map, is like way. Now as each cells in Keymap are organized in group in gray code order, just one bit position can change of literals between two consecutive cells. That means this value is a 4 variable map. The first cell value is the 0000, that is the 0001, that is 0011, that is 0010. Look at that the one bit change, it is 1. From that is one another bit change, that is 1, and this one another bit change is 1, 0. That means in row wise or in column wise, just one bit has been changed, nothing else. So in that case the Hamming distance among two cells is 1. So the min term max term representation in Keymap is explaining here. So in order to obtain the simplified expression in SOP, to the each min term in given function must be 1, will be entered in the corresponding cell, but in case of max term will be, it is equal to 0. That means 0 will be entered in the corresponding cell of this Karnaugh map. Now this important thing is that is the map covering rules. So first rule is that number of covered literals must be equal to 2 to the power n, where n is the non-negative integer. That means we have to cover those literals. Suppose we are taking a 4 variable map, that is A, B, that is C, D. According to the first rule, number of covered literals must be equal to 2 to the power n. So here is the literals in SOP expression. Literals means, suppose we are taking some functions, that is 0, 1, 2, 3. So here 0, 1, 2, 3 are the literals, and in that case this 0, this 1, this 2, this 3 is there, and rest of the same will be treated as a cross. It's not there. Now I have to map those literals. So according to the first rule, number of covered literals must be equal to 2 to the power n. So 2 to the power n means here are the 4, n is equal to 4, so 2 to the power 4 means 16. So this case is 1, 2, 3, 4, and this satisfies 2 to the power n because it is 4, 1, 2, 3, 4. So this can be mapped. Number 2, use minimum number of covers to accommodate maximum number of literals. So I have to use the minimum number of covers that will accommodate maximum number of literals. So in this example, if I would like to cover this way, this one, and this one, here extra 2 covers are there, but in that case I have to use the minimum number of covers. So in that case we are covering as a whole. Number 3, diagonal covers are not allowed, but folding covers are allowed. We can't cover literally in that way. We can't cover. But folding cover means this cover, this cover, this cover, this cover, that can be possible. Overlapping of cover is allowed, that is 2 covers can have 1 or more ones is common, At the same time, redundancy is not allowed, that is, a cover whose all ones are overlapped by other covers. That means if we cover like that, it is not allowed. Here, this one, this value is covered by this cover, this cover, this cover, and this cover. It is not possible. So in that case, I have to cover only one. That is either this one or this one, but not the both. And the 5 one is that the literal covering is possible if and only if their bitwise exclusive OR value is realized by 2 to the power n. That means we can cover only this kind of literals if their XOR value must be realized by 2 to the power n, otherwise we can't cover. So this is a covering types. The first one is a pair. It is a pair. The second is the quad. This quad, 1, 2, 3, 4 quad. Like this quad, this is quad, and this is quad. This is octet. Octet means 8 literals at a time. Octet. And this is the summary of Keymap. That is, enter a 1 on the Keymap for each fundamental product that corresponds to output 1 in the truth table, and blank out stands for 0. Second one is the encircle the ones as octets, quads, and pairs in that order, and encircle is the isolated one also if any exists there. And this is another rule for Keymap, and this is applicable for POS form. In case of SOP, we can map with number of ones, and in case of POS, we can map by zeros. And this is the example of a function, of a 3-variable function, that is ABC, that is equal to 3, 5, 6, 7. Here we are using 3 min terms like that, 1, 1, 1, 1, and 1, 1, and we can get this equation like that. That is 3, 5, 6, 7. So that is 0 value, that is 1, that is 3, that is 2, that is 4, that is 5, that is 7, that is 6. So 3 means this one, 5 means this one, 6 means this one, 7 means this one. And this is a cover, this is a cover, and this is a cover. So from the first cover, C1, is the second cover, C2, and this is the third cover, that is C3. So from C1 we can get this one. So here we can choose the following value where we can get the common element. So in that case we can get, that is BC. From C2 we can get, that is 1 is common here, and that is A, that is AB. And from C3 we can get, that is 1 is common, this one and this one, and this is 1, that is AC. So the result is like that, C1 plus C2 plus C3, that is BC plus AB plus AC. So this is the output of this following function. So now, y is a function that is b prime plus ac prime plus a prime cd, that can be realized by this 4-variable Keymap, and it is this like way. So here we can find the b prime. So what are the b prime? From this section we can notice that a prime, b prime, that is 0 means a prime, 0 means b prime. and from this one we can get 1 0, that is A, that is B, sorry, A, that is B prime. So here B prime and B prime is common, but A, here is A prime and here is A. So we take only the B prime here, because if we take these values like that, that is A prime plus B prime, and from this one A B prime. So if we take B prime as a common, so A prime plus A, that is equals to 1, so we get the B prime only, that is B prime. And that is A prime CD, that means these two cover, that is means 1 1, that is means CD, and from there we can get A prime, because A prime is common here. Here is A prime, but there is B prime and B, so it will be eliminated and we get the A prime, so it can make the A prime CD. And from this we can get A C prime, that is C prime, that's 2 0, that is C prime, and from above is called the A, so we get the AC prime. So the all over expression will be like that, that is B prime plus AC prime plus A prime CD. So this is a 5 variable map, and this is the 6 variable map. So they are not used in real life for handwork. If you wish, you can try at your home to large number of literals, to take large number of literals. And this is the summary of today's lecture. So now we can conclude in this regards that today I have taught the fundamental concepts of Boolean algebra, to learn about Boolean axioms and laws which will be useful for expression simplification, to learn about Boolean function generations and function representations in terms of SOP and POS, and last of all to learn about the Boolean function minimization by using Karnaugh map. So thank you to everyone.